How's it going?
Excellent.
It's going.
It's going.
This is my last class today. Sam, what are you doing? Second time, man.
Morgan asked me a question about one of the ones out of the text, so let's look at that real quick. I try to break the class. That's 1.2-8 on page 19. So you've got the probability of A is 0.4. Probability of B is 0.5. Probability of A intersect B is 0.3. So part A asks you for the probability of A union B. So how would we attack this one? Cool. Yep, I agree. So we'd have 0.4 plus 0.5 minus 0.3 gives us 0.6. We okay with that? Second part asks for the probability of A intersect B complement. Couple of ways to get at that. Probably the most straightforward, at least for me, would be to draw the picture and figure out what region we want, and then see if I can fill in values from that. So if I have A, I have B, I have handout. All right, we just found that the inside here is 0.3. That should help us label two other, well, actually all three regions, but two other ones pretty quickly. The entirety of the circle A should be what? 0.4, right? It tells us the probability of A is 0.4. So the entirety of circle A should be 0.4. How much of A have we already filled up? 0.3, so what's left? 0.1, and that should give us what we want now, right? Because what we want is probability of A intersect B complement. That's the stuff in A and not in B. Is that the number we just filled in? So that should be 0.1. Yeah.
What's concerned about like everything outside of it?
When are we?
Yeah, like why?
It is included not B. It's just that it's an intersection. Because not B would be everything and this part. So we want the part of that is just in it. So that's just that piece. We should be able to fill in the rest of this. The entirety of circle B is what? 0.5, and again we've taken up 0.3, so 0.2, and then we should also be able to get out the outside region then. Why? Good. Or the outside region is the complement of the union, right? So the 1 minus the 0.6 is exactly right. So we should have 0.4. There's nothing that you said was wrong.
No, I said that your way was a lot easier.
Oh, yeah. Yeah. It was a lot faster. It was just faster. All right. So now that we've got the rest of this filled out, it should help us answer the other one. So part C asked for the probability of A complement union B complement. Either we can use the formula again or just look at the picture. It's everything in A complement along with everything in B complement. Thinking about the picture, what's missed? What's not in that set? the intersection is not in that set, right? It's everything outside of A put together with everything outside of B. The stuff in both of them never gets put in there, right? So, and that's actually what's referred to as De Morgan's law. This is the probability of the intersections complement. That's De Morgan's law. We can flip that around. And this would just be the complement of the intersection, which is 0.3. So this must be 0.7, 1 minus the 0.3. Yep, you can take everything outside the intersection and add it together. It's good.
How does that work exactly? Because to me, just based off of looks, it looks like everything that's not in either A or B. So I would assume it's 0.4 outside. So how does that work?
So remember, union means you put it's in one or the other or both. So everything that's outside of A, if you think about the picture, everything that's outside of A would be that shaded region, right? And then B is in here. So notice that this part gets shaded at the same time. And then with union, remember I don't erase anything or double shade. I just worry about everything that's along with it. So if I shade outside of B, I get all of this stuff.
Okay.
So the only thing that I miss is that part in the middle. The way you were thinking about it is that. That's everything that's outside of both sets.
Okay.
It's a good question, because it's easy to be confused with it. This one okay? Or other questions? Or say quietly? It's always an option. All right. Well, let's do some more that involve the counting stuff that we talked about last time. So on that sheet that I just handed out to you at the beginning of class, let's look at 2.1. I think it's a lot easier with some of these just to do problems. There's not a real hard and fast rule of how to attack different types of problems. Your big things that you have to remember are repetitions allowed or not? Is order important or not? Okay. So we'll be looking at using multiplication principle, doing one task after another, we'll multiply things. We'll be looking at either or situations where we'll add things together. We'll be looking at no repetitions and order matters, so we'll have permutation. We'll be looking at no repetition, order doesn't matter, we'll have combination. So it'll all just matter from the context of the problem, how we attack it. And like I said, I think a lot of it is just get in there, start doing some types of problems, and see how to attack it. Okay. So looking at 2.1, it says we have a box that contains 4 blue, 5 white, 6 red, and 7 green balls. We're going to draw samples of size 5, and it asks us how many ways can we represent every color. So what is a way, what are some ways that you might try to attack this type of problem? Just make sure you have at least one of each color. Good, Chris.
Is this looking for?
Yeah, it's looking for a number. Yeah, it's not. This one's not a probability. It's just looking for a total number of ways to do it. Okay, let me ask you this. Let's start with an easier question. How many ways can you draw 5 balls total? Period. Not with any restrictions at all. Well, how many total balls are there? How many are we choosing? 5 without replacement, right? So no repetitions. Right? Okay. How many total ways would there be to do it? Well, what kind of object would you have then if you're doing without replacements in the order matter? It would be a combination, right? So the total number of ways to draw is 22 choose 5, right? Do they have a number for that? 26,000, what was it? 4? Okay. Which is a good thing. Well, I guess it's not such necessarily a good thing. It doesn't eliminate any of the possibilities, right? Because we're doing a subset of that, a piece of it. But at least it gives you an idea. So certainly, if you didn't have the choices there, certainly you would, if you had a number now bigger than 26,000, you would know that you did something incorrectly, right? All right. So we want to make sure that each of the colors are represented, right? That you have at least one of each color. But it's also possible that you could do you have 5 balls, you're going to have to do 2 of one of the colors and 1 of the other ones, right? Just from the way the outcomes have to happen, right? There's 5, you want 5 balls, there's 4 possible colors, right? So you can't have 3 of one color because you would run out of choices for the other 3 colors, correct? So one way to attack this, at least in my estimation, one way to attack it would just be brute force, do the possibilities. What are your possibilities if you're going to have all 4 colors represented? What are your? There's 4 possible ways you can do it. What are they? Okay, yeah, there's 2 blue, and then the rest have to be 1 of each, right? Or 2 red, or what are the other colors? White, green. Okay? But then there's 1 of each of the other ones, right? We agree? So how many ways are there to choose two red balls? Red was, well, okay, blue, whatever. I guess blue was the first one, sorry. I was trying to go in order, I thought red was first. I don't know why. And 1 of each of the others. Well, the and one of each of the others should be pretty straightforward. How many ways are there to choose one white ball? 5. 1 red, 1 green. 7, right? From combination language, I could think of it, and again, the order doesn't matter, right? So I would have 5 whites, I'm going to choose 1. I've got 6 reds, I'm going to choose 1. 7 whites, or greens, sorry, I'm going to choose 1, right? That's just one of each of the other colors. How many ways are there to choose 2 blue ones? 4 choose 2? Good. Yes, it is 6. Just writing it as a formula. That would be what it is, right? Just as a formula, correct? And again, we can think of this as multiplication principles. We can think of this as tasks. Choose the blue, then the red, then the white, then the green, or whatever order it is. I think it just said the red and the white backwards, but. Okay. So you would have 6 times 5 times 6 times 7, whatever that number turns out to be. What was it? 1260? Yeah, that makes sense. Now we should be able to have the formulas for the other ones, because this was the case where you had 2 blue and 1 of each of the other ones. Right? Right? So what if we had 2 white? That was the next one, right? What would the formula look like? 4 choose 1, 5 choose 2, 6 1, 7 1, right? I'll give you 1680. Did I add it right? Did I multiply right? What's the next case? 2 red. Yeah, so we'd have 4 choose 1, 5 choose 1, 6 choose 2, 7 choose 1. What do you get for that number? 2100? And then finally, the 2 green. 4 choose 1, 5 choose 1, 6 choose 1, 7 choose 2. What is it? 2520. Then what do you think you're going to do with those 4 numbers? Add them up. Because again, we've got mutually exclusive ideas, right? I can't have 2 green and 2 blue at the same time in 5 balls if I'm going to have all the colors represented. Right? So these are mutually exclusive ideas. If you add them all together, what do you get? 7560, which is one of the answers. That's always good. So this was just brute force going through the different cases. It's not bad because they're all following the same pattern. And the numbers aren't horrible where you have to add the numbers up or anything. You could have also thought about it as the complement idea. You could have thought, okay, how many ways are there to get no greens? It's just sometimes complement is the way to go. It makes it a little bit easier. But I think a complement in this case would be a little bit more difficult. You could do no greens, but 1 of each of the other 3. And then the same thing with white and red and blue. But then you also have to say, okay, what about no green and no white? no green and no red, no green and no blue, all those kind of things. When you start thinking about all the possibilities of having at least one of the colors not represented, it's going to be a mess, right? So I think this idea is a little bit more straightforward. But typically in these problems, there's more than one way to attack them. Sometimes it takes a little bit more ingenuity to get through it than others. Sometimes you want to look at it as a complement, count up the things that you don't want and subtract it off. But no matter how you do it, if you're thinking about the problem correctly, you should get the same answer. If you went through this and said, okay, I want to calculate no greens, but at least one of each of the other three, and then do the same thing for the whites and the blues and the reds, and then do all the other possible combinations and add it up and subtract it from the total, you still should get 7560. It's just going to be a lot more work to do it. There's a lot more cases. Does that make sense? Let's look at the next problem, the 2.2. Notice in this case they're leaving it in formula form. So we're looking for a number of batting orders for a co-ed softball team that they're going to alternate the batting order by gender. What are your thoughts on this one? Do you have a thought, Chelsea? Mm-hmm.
Do this problem like that because you have 10 different possibilities. The one has to start first.
Okay. So you've had 10 different slots. Okay.
And then after that, you can't have the same one start first. You have 9 different.
Okay, so I think the way you're thinking about it is okay. So the woman has to start first. How many women do you have to choose from, though, for that first slot? 5, right? So it'll be 5 there. This can't be a woman. The next one's a woman, so this would be 4, skip, and then 3, skip, and then 2, skip, and then 1. Yeah. Anything different for the guys? No. So it'd be 5, 4, 3, 2, 1, right? So we can absolutely think about it as those tasks like we did the telephone numbers. Yep, and fill in the slots. What will we do with all these numbers? We multiply them all together, right, to get the total. So we can see this, hopefully rearrange it to get to the answers that you want. I certainly see a couple of 5 factorials, right? So right away, even before you do any simplifying, if you do it this way, you should be able to throw out 2 of the answers, at least 2 of the answers. And one is just a single 5 factorial for A and a 10 factorial for E, right? Neither of those make sense for the way we set this up. There's also a 10 factorial in D. That means throw that one out too, right? So it's a matter of, is it 2 times 5 factorial or is it 5 factorial squared? It's a 5 factorial squared because it's all multiplied together, right? There's a 5 factorial times a 5 factorial. So 5 factorial squared. We could have also thought of it as just multiplication principle as two tasks. Kind of how I actually wrote it down, right? First pick the women, then pick the men. There's 5 factorial ways to order the women, 5 factorial ways to order the men, and then multiply them together. If you're thinking of taking an actuarial exam, for exam P, sometimes I leave the answers in terms of formulas. That's where I got these problems, by the way, from an actuarial review manual. But they'll leave them in terms of the formulas rather than just a final answer. So along those same lines, let's look at 2.6. I can. Would you like the answers? Yes. Well, for some of them, because some of them I'm going to give you for homework problems. They turn in. All right, so 2.6 has a box with 10 white and 15 black marbles. You're going to select 10 total marbles, and you want the probability that x of the 10 are white. So notice in this particular problem, you're not actually given an x. You're not figuring out, that 3 of them are white. You're giving an x so that you have to come up with a formula. All right, so before we do the formula, it's asking us for a probability, right? As soon as we know we have a probability, I need to know the size of my sample space. I need to know the denominator. If I don't know the denominator, I can't do the probability. Agreed? Okay. So let's do that first. How many total ways are there to choose 10 marbles? With no restrictions, not worrying about the colors. How many ways are there to choose 10 marbles? There's 25 total, right? And you're choosing 10. It is without replacement, and I'm not worried about the order, right? I'm just worried about how many of a certain color there are, correct? So the total number of ways to choose 10 marbles from 25 is 25 choose 10. And again, the reason why it's 25 choose 10 is because there's 25 total marbles. We're choosing 10 without replacement. Order doesn't matter. Just count the number of colors. Does that make sense? Okay. So before we think about the formula, let's think about a specific example and see if we can generate the formula. Because this particular formula is going to be one that we're going to see later on in the semester called the hypergeometric distribution. So let's see where this formula comes from. So let's go back to my specific example and say we wanted the number of ways to select exactly 3 white marbles. Let's give it a specific number. I just picked 3 out of a hat. No, I didn't actually pull it out of a hat. That's the same. I could have pulled it out of a different place, but let's say out of that. All right. So let's think about how we would have to fill this in. Let's think about first just picking the white marbles. How many ways are there to pick 3 white marbles? 10 choose 3, right? This is literally just picking the 3 white marbles from the 10, correct? But that's not picking 10 total marbles. How many marbles are there left to pick? 7. Where are those 7 ones going to come from? The other one, whatever, was it black? Okay, good. I didn't remember the color. the other 7 have to come from the black marbles, right? How many ways are there going to be to choose 7 black marbles? 15 choose 7. And again, we can think of this as tasks, right? First choose the white, then choose the black. Correct? So we would multiply those two together to give us the total number of ways. And then we would divide to get the probability, right? This would be your numerator, this would be your denominator. We agree? All right, so let's see if we can extend this now to the answer, right? We did a specific example of 3 white, so then we had to do 7 black. Well, instead of 3 white, the problem asks for X white, right? Well, if X of them are white, how many of them are black? Then minus X, right? So instead of having 10 choose 3 and 15 choose 7, what should we have? 10 choose X and? Good, exactly right. Do we see that in one of the answers?
Yes.
Which answer is it? C. Yeah, cool. So there's our probability. Okay? Let's look at one more here. Let's look at 2.13. You're going to roll 4 dice. You want 2 identical odds and 2 identical evens. Think about it for a minute. That happens from time to time, too. Get the double arrow. I don't think your numerator is right. But your denominator is not right. Then hit the
I thought it was way easier than everybody else. So you just have no more dice. The way the problems are is that really you're just getting loads of symptoms with like word. So you've got 6 possibilities. Right.
I'm not sure how you're getting 24 from what you're explaining to me.
I took 6 times 4, which number right. You've got 6 possibilities for each dice, right? You've got 4 dice. Yeah, but I'm just
Yeah. You know more about how you thought about it.
no,
So that doesn't sound like I was thinking about it, right? And having a game in the
next one. Proof number 5.
Yeah, you did.
So I did it wrong.
I'm still not sure why you did 6 times 4. Besides that, you took 6 possibilities times 4 dice.
Yeah, that's what I did.
Yeah, that doesn't sound right.
I think I got the answer.
What did you get?
A.
I don't think it's A, if I did my math correctly.
Did you use it using choose or did you use it using just
Say it again.
Did you use it using choose or just using
I did it, well, I had to do some choose.
Well, here, let me show you the way I did it.
Okay. I did my math correctly. I did it in my head. So that was a possibility.
So 4 dice. So first, you want to make a claw. So first, you get 1 off.
Okay.
I think that's the problem with that. Is 3 over 6. I'm getting just getting off.
Okay.
And then to get that same one, same number, one option,
Right, but there's other problems that you don't, but I think you're not doing the order. I think you're doing like die 1, die 2, die 3, die 4. I think you got a lot of possibilities. I think that's where, so that'll work because then you have to get the other possibilities. I think there's other possibilities that you can multiply by. So the 1 on 144 is not bad. It's just, you're thinking about it a good way. It's just a matter of having it work. And when it has to be the same as the previous one, you literally only have one choice. So we're going to
That's the right answer. And on both tests,
it literally has to be the same. Yeah. So if you roll a 6 on the first one, you have, if you want, if it's going to be the same as the 6 on the second one, 6 on the first one, you want the same as the second, there's only one choice. Right.
you want one.
Okay.
And that doesn't work, yeah.
So,
Yeah. I agree, that doesn't work. It's not. We'll talk about why. Because you're thinking about it right. There's just one more way. You're thinking about it the right way. Yours is very close. There's just one little extra piece. Say that again? It's yes, of some sort, yes. All right, let's talk about it. No, I want to talk about it. I'm talking about Grace. You can be patient. All right. So what I wrote on the board is the total number of ways that you can roll 4 dice, right? There's 6 ways to roll the first one, 6 ways to roll the second one, 6 ways to roll the third one, 6 ways to roll the fourth one. So that's 6 to the 4. Your denominator needs to be 1296. The numerator is what's giving everybody fits. All right, so let's just think about one very specific case. Okay, what if you had odd, odd, even, even? For the way it was, so die 1 was odd, die 2 was same odd, die 3 was even, die 4 was same even. What would be your number of possibilities? Well, I have to get an odd. Are there 6 odds?
3 choose 1.
Yeah, there's 3 odds, so it'd be 3 choose 1. Yeah, because there's only 3 odds, right? Right? There's only 3 odds on the ballot. And then the same thing for the even. If I have to get an even here, what's that going to be? 3 choose 1, right? We agree? Okay. Now, once I have this odd, this one has to be the same. So once I have this one I have no choice, right? It has to be 1 choose 1, right? There's only one that matches it. And then the same idea here. Okay? But notice I wrote this down as a very specific case, right? I wrote it as odd on the first, same odd on the second, odd even on the third, same even on the fourth. Is that the only way you're going to roll the 4 die? Come up with the same result? No. For each of these, you could have done odd, even, right? Or odd, even, odd. Even, odd, even, odd, even, right? How many different rearrangements are there of these? So it's close to the 4 factorial. Because some of them look the same, right? It's 4 choose 2, right? I've got 4 spots, I'm going to put the odds in 2 of them. So I've got to multiply this by 4 choose 2, and that was the factorial type of thing that you were talking about, Alex. So this is, I've got 4 slots to put in. I've got 4 places where I can put the odds, and I'm going to choose 2 of them. So this turns out to be 6 times 3 times 3. So you had 54 on top. Yeah, 54. So you get 54 out of the 1296, and I think that's 124. Yeah, crazy.
So is that 4 over 2, or 4 choose 2, assuming that order matters. The order of which
It does, yes, because the sixth to the fourth implies the order. If you're counting number of ways to roll the first die, number of ways to roll the second, third, fourth. So that 4 choose 2 is the number of distinct rearrangements that give you the same result.
So we're not, the odds are not.
Correct.
Oh,
Yeah, the odds are going to be right next to each other, so you have to count the number. But the odds being identical means that I can't tell the difference between odd on the first. If I'm going to rearrange them, and if I rearrange them as odd, even, after I think of it as just odd, even, I can't tell the difference between the two odds. I don't know if it was first and second, or first or second and first. It doesn't really matter. So that was why it's 4 choose 2. You're just thinking about filling an odd in a spot and then filling another odd in a different spot. So you got 4 slots to fill in. You're going to choose 2 spots in which to put the odds. So there's 6 ways to do that.
So like the idea that we were talking about, like the 6 choose 3, is that just because we can't do that because it's not certain that it will give you?
It's not certain that it'll give you the odds.
Yeah, that's okay.
Yeah. So you got to actually pick from the odds. All right. All right. Let me give you some problems for homework. What do I want you to do? This was on here. Oh, there's some from the packet too. I think I did the one out of here that I wanted you to do. So yeah, from the packet here, I want you to do 2.5 here. 2.5, 2.9, 2.14, 2.17, and 2.19. And we'll make this due on Monday. They're on the board.
I said the same.
Oh, I didn't see it.
I was trying to write.
They're on the board. It was Monday the 9th.
So just those problems?
Yeah. Yep. All right, have a good one. We'll see you Friday. We'll get into the next section. We'll see ya. See ya.